So in this video, we're going to look at the results of solving the Schrodinger equation for the hydrogen atom. So remember in our last video, we learned that there was this mathematical formula that was invented by Erwin Schrödinger. Well, not invented, but he thought of the idea. That describes the behavior of particles at the smallest level. So we're trying to describe the properties of the electron in the hydrogen atom. We looked at the Bohr model and discovered, well, that works well for the hydrogen atom, but not so well for other kinds of atoms on the periodic table. So Schrödinger came along and took some of the new ideas that were buzzing around at the time and came up with this idea of quantum theory. And so he has this fundamental equation, his wave equation. And what we're going to do is solve that for the hydrogen atom. And so what we get out of that are, one, energies, quantized energies. So the electron in the hydrogen atom can have only fixed energies, nothing in between, only those fixed values. We say that they are quantized, rather like channels on a television that you can only be on one channel, not in between. Whereas a volume knob, oftentimes you can set that anywhere you want, right? Okay. So that's one piece. The other thing that we get out of solving the Schrödinger equation are these things called wave functions. And last time I told you that those guys were, so it was represented by this Greek letter psi. So there's the Greek letter psi. And in order to keep track of the wave functions, and actually these numbers come out of quantum theory too, we have these quantum numbers. There's a principal quantum number n, there's an angular quantum number L, and then there's a magnetic quantum number m sub L. And remember, we've learned that n, can take on only certain values. N can be 1, 2, 3, and so on. L starts at 0, counts its way up to n minus 1, and m sub L starts at negative L, count your way up in integer steps past 0, and all the way until you're as large as positive L. So this describes a particular wave function. And what we'd like to do in this video is look at what these wave functions tell us. So remember, I told you that if you take the wave function, which is just a mathematical equation, and you square it, that tells you something about the probability of finding an electron somewhere. It's the probability of finding an electron somewhere. So we would like to think about how we could look at this mathematical function, how we might sort of graph it and look at it. So we're going to look at 3 different kinds of plots. Actually 4, let me take that back. We're going to look at 4 different kinds of plots. So the first kind of plot is called a radial plot. And so in all of these cases we're looking at a hydrogen atom. So right here, let's imagine here's the nucleus. There's our 1 proton. And we want to know something about where this electron is likely to be located. And so what we're going to do is just draw a little arrow, call that distance r. That's the radial distance, so that sort of looks like an R, doesn't it? Anyway, that's the radial distance from the center, the nucleus of the atom. And so we just want to do a plot of probability on this axis. And remember, that's just going to be the wave function squared versus r. So when r is equal to 0 right here, well, that's right on top of the nucleus. And we want to see what things look like as we move further and further away from the nucleus. So what is the probability of finding the electron some distance from the nucleus? That's what this kind of plot will tell us. So that's a radial plot. Another kind of plot that we're going to look at is called a dot plot. So in a dot plot, what we see are little dots, and the density of the dots in space tell us something about probability. So if we've got a lot of dots in one area congregated in the middle, then that's a high probability, whereas if we're further away from some area and the density of the dots is not very high, then the probability is low. So in this little dot plot that I've just given you, the probability is higher in the middle and lower as we go further away. We can see that more clearly in this picture. So imagine that we've got this little ink sprayer. So we've got some sort of dye inside here, and we squeeze the bulb and it sprays ink out. So most little ink droplets fly straight ahead and hit the screen right about here. Some, though, get scattered pretty far away. And so this is an example of a dot plot. What is the probability of finding an ink droplet somewhere in space? Well, we can kind of see that the highest probability is going to be here in the middle of this circle, right? And then as you move further and further away, the probability falls off. So when there are lots of dots congregated together, that would be high probability. So that's what we mean by a dot plot. So that's another kind of plot that we can look at in 2 dimensions. A third kind of plot that we're going to look at is something called a radial distribution plot. Sometimes it's called a radial probability distribution plot. And we're going to look at how that is described on future slides. So we're going to go in and look at that. And then our fourth kind of plot that we're going to look at is something called a contour plot. And again, I'll explain what a contour plot is on a future slide, so we'll get to see these plots. So what we're going to do now is go through and look at these four different kinds of plots for these different kinds of functions. So what we want to do is for the hydrogen atom, we're going to choose the different values of the quantum numbers and look at what those different wave functions look like. So our first set of wave functions to look at is the one where the quantum number is as small as possible. So we're going to choose n equals 1. So if n equals 1, L can only ever be 0. And if L can only ever be 0, then m sub L can only ever be 0 as well. So we're going to look at this n equals 1, L equals 0, m sub L equals 0 plot. Now there are lots of numbers here, and so chemists have come up with sort of a code to use for the L values. So I'm going to teach you that code right now. So what we're going to have is the L quantum number, and we're going to list those values as a little table here. And then we have a little symbol that we use instead of this number. So when L equals 0, the symbol that we're going to use is S. When L is equal to 1, the symbol that we're going to use is P. When L is equal to 2, the symbol that we're going to use is D. These are all lowercase letters. When L equals 3, the symbol that we're going to use is F, and alphabetically after that. So L equals 4, we're going to use G, and then it goes H, I, J, and so on. So these are the symbols that we're going to use to correspond to these different L values. So you may hear people talk about the wave function as being a 1s wave function. So that just means that the n quantum number is equal to 1, and that the s is telling you that the L quantum number, right here, S means 0, that the L quantum number equals 0. So that's what that means. So you're going to see some of that notation in these next slides. So let's go and look at some of the plots. All right, so here we are. We're looking at the hydrogen atom ground state. So this is the psi 1, 0, 0 wave function, also known as the 1s wave function. So the first plot that we're going to look at is that radial plot that I told you about. So this is a radial plot. So it shows us the probability of the electron being at some point. So this is psi squared versus distance from the nucleus r. So right here, this point right here, that's 0. So that's where right on top of the nucleus. And you see that the probability is highest right on top of the nucleus. And then it goes down as we get further and further away from the nucleus. So that kind of makes sense, right? The electron is probably going to want to stay close to the nucleus because plus likes minus. And this shows us that the probability of being far away from the nucleus gets progressively smaller and smaller. And you can see that here in this dot plot. So they're really cool things that you can find online that show you these dot plots in 3 dimensions, and you can actually grab a hold of one and rotate. But you see that the highest probability is here in the middle, right at where the nucleus is. That little black dot would be the nucleus there in the middle. So the highest probability of the dots, the highest density of the dots, is here in the middle. And then as we go further and further away from the nucleus, the density of dots gradually decreases. Okay, so that's a dot plot. So the next kind of plot that we can look at is called a radial distribution plot. So it's the radial probability distribution, the total probability of an electron being in a spherical layer. What does that mean? All right, so let's imagine that we take our whole atom and we're going to break it up into these little spherical shells. So these are like skins on an onion, okay? So see this little circle right here? Well, inside this circle, right, we're going to ask, well, what is the probability that you're inside this circle? Now, it looks like a circle here in 2 dimensions, but in 3 dimensions, this would look more like a shell with a certain thickness, like an onion skin, right? So we're asking, what is the probability that an electron is some distance r, located in a shell, some distance r from the nucleus? So you're in a little shell, some distance r from the nucleus. And the way we calculate this is we take this probability, psi squared, and then we multiply it by the volume of this shell. So as we move further and further away from the nucleus, the volume of the shell increases, right? Because the radius is going bigger, so there's much more space say, in this layer here on the outside than there is here in this layer on the inside. And right in the middle, right where the nucleus is, the volume of that shell, well, that's going to be 0. So we're multiplying the probability times 0. And so a typical plot looks kind of like this. It goes up, has a peak, and then it comes back down. To give you another kind of analogy to think about what this radial distribution plot might look like, let's look at this probability. So this is the radial probability distribution of apples falling from this tree. So here's a tree. So these apples are going to fall down at this tree. Every now and then one will bounce kind of far, or maybe a squirrel will grab one and carry it far away before dropping it. And so we get kind of this distribution of apples. So what we're going to do is go in and mark off on our on the ground rings that are equally spaced a certain distance from the apple tree, the trunk of the apple tree. And then we're going to go in and we're going to count the number of apples that are in a given ring. Okay, so we count the number of apples. So right here, right where the trunk of the tree is, there are no apples that can fall there, so it's 0. And then in this first ring, we have several apples, but because the ring is kind of small, they're probably not as many as there are out here. And so the number goes up and peaks, and then as we move further and further away, the rings get progressively bigger, but the chance of finding an apple out there is kind of small. And so this little peak right here tells you sort of the ring that has the most apples in it, where it's most likely in one of these rings to find an apple that has fallen. So that's rather what our radial probability distribution is showing us. It's kind of showing us, if you thought of the atom as being broken up into shells, what is the most probable shell? The most probable distance. And it would be right here at this peak. So if the atom were broken up into shells, this right here, this distance, if we go down to r, that's where you'd be most likely in what sort of ring around this nucleus to find an electron. And so this is the result for the psi 100 wave function. So we get that. Now let's talk about a contour plot. So that's our other kind of plot that we haven't yet talked about. So this is an example of a contour plot. So what we do with a contour plot is we try and get an overall idea of the shape of this orbital. And like contour maps on topographic maps that show you the contours of the ridges and the valleys and the mountains, what we're going to do, those are lines on a contour map at constant altitude. So you draw little lines at constant altitude. What we're going to do on this plot is we're going to look at one of these dot plots, and we're going to draw a surface on that dot plot so that we enclose like 98 or 99% of the probability, 98, 99% of the dots. And the probability of finding an electron anywhere on that surface is going to be the same. So that's a contour surface. So if we draw that shape for this 1s orbital, what does it look like? It looks like a ball or a sphere. So 1s orbitals, and this is the important take-home message to remember, look like spheres. So it's a ball. The nucleus is in the middle. As you move further and further away, the electron density goes down and down, and the way that this ball is drawn, let's say 98% of the time, you're going to find an electron somewhere inside that ball. The probability of finding an electron anywhere on this surface, everywhere on the surface, will be exactly the same. So that's how we draw that. So there's a contour plot of the 1s orbital. So now let's go and change some of these other quantum numbers. So now we're ready to move up to, well, we'll do it on the next page. Here we go. So here's the 1s. That's the one that we just looked at. Here's the radial plot, n equals 1, L equals 0. Here's a dot plot and a contour plot. So this is kind of a section of a contour plot. Remember, it's a ball, so we just kind of cut a little wedge out of the ball. And here's that radial probability distribution plot. Remember the apples from the tree kind of plot? So that's that plot for the 1s orbital. Now we're ready to look at what we call a 2s orbital. And so that's for psi with n equals 2, and we're going to let L equal 0. And that means m sub L can only ever be 0. So this is called a 2s wave function. Remember, when L is equal to 0, our code, we're going to use S for that. So this is called a 2s orbital. Alright, so what do we notice about this? So the radial probability looks kind of the same. It falls off and then it goes to 0 right here, dead at 0. But then it climbs back up again. And then the probability falls down as you move further and further away from the nucleus. So this little point right here is kind of an interesting one, so I'm going to draw an arrow to it. The point where it goes absolutely to 0, that's called a node. N-O-D-E. Technically, this is called a radial node. So everywhere, when you're at that distance from the nucleus, the probability of finding an electron there is 0. Not just close to zero, zero. That's what quantum mechanics says. So here's a dot plot picture. So you see the dots are really concentrated, and this looks more like a fog. These dots are really tiny, but the dots are really concentrated here at the nucleus. Again, that's the highest probability. But then there's this region of zero probability, this kind of ring. So this would be kind of a shell around the nucleus where you don't see any probability at all. Then as we go further out, the probability increases and then finally gets small again. But again, what's the overall shape? It's a ball, right? So this is just a wedge that's been cut out of that ball. So it's a spherical shape. How does the contour plot differ from the 1s? Well, it's bigger, right? So we've increased the typical distance away from the nucleus. So it's gotten bigger. Down here we see the radial probability distribution plot. So what does it look like? So again, it's zero at the nucleus because the shell at the nucleus has zero volume. So you multiply that by psi squared and you get nothing, right? And so then it goes up a little bit, but then it comes back down when we hit this little node. And then it peaks again, right? It's pretty big out here because the shell has a lot of volume when we get out there. And so this would probably be the most probable distance from the nucleus. Hey, this kind of looks like orbits, a little bit like Bohr's orbits, right? So here we've got an orbit that's really close to the nucleus in the 1s, and the next orbital, the distance from the nucleus is further away, more like 3 times 10 to the minus 10th meters, 3 angstroms. Whereas up here we were more at about 1 angstrom, or half an angstrom, 0.8 angstrom, something like that. So we're kind of moving further away from the nucleus. This is our most probable distance. So n equal 3 also looks kind of similar. Here's our radial plot, comes down, hits a node right there, climbs back up, hits another node. So the n equal 3 has 2 nodes, right? 2 nodes. And here are those nodes shown on this dot plot, and also the contour plots there. And here's what the radial probability distribution looks like. So for n equal 3, we have 3 bumps, 2 nodes, and this is our most probable distance then from the nucleus. So you're most likely to find an electron in a shell about this distance from the nucleus, about 7 times 10 to the minus 10th meters from the nucleus. But again, the overall shape looks like a ball. And as we increase n, because we're not changing any of the other quantum numbers, what happens? We just increase the size of the ball. Now I want to point out one other very curious feature about these nodes right here. So these are actually regions of zero probability. So remember, the hydrogen atom has 1 electron. So if the hydrogen atom electron was described by this wave function, the psi 3s wave function, then what we're saying is that 1 electron has a really good chance of being really close to the nucleus, has a pretty fair chance of being like about 2 angstroms from the nucleus, and if we look at a shell that's about 7 angstroms from the nucleus, well, there's a really good chance that you'll find an electron somewhere in a shell that's that distance from the nucleus. But right here, there's 0 chance of finding the electron that distance from the nucleus. Wait a minute. So if the electron can be here with a good probability, or it could be here at about 2 times 10 to the minus 10th meters, how does it get from here to here without ever passing through this point right here? Because it's got to have 0 probability. So how does it move from one side to the other? Well, here's the Heisenberg uncertainty principle that says we can't say with certainty both where an electron is, its location, probable location, and how fast it's moving, or how it's moving at all. So we can't know that. We're infinitely uncertain. So quantum mechanics says we can't ask questions about that. So just stop. You can't ask a question about how an electron, if you know its probability distribution, how it moves around to get that probability distribution. So this is just one of the weird features of quantum mechanics, that we can't get a good answer to that question. If we ask about how the electron is moving, we can do that, but then we're going to lose all information about where it is probably located. Oh, man, really? Yeah. So quantum mechanics is confusing. This is why there are graduate school courses in this whole field, right? So for our purposes, we just kind of need to know what these wave functions look like. So S-type wave functions look like balls, and as we increase the n quantum number, what happens? The ball gets bigger. Here's another picture from your textbook that just shows the same picture. So here are the dot plots that we were looking at, kind of sketched in where that contour would be on the outside surface of the sphere, and here is the probability distribution, which is just the area of the volume of one of those shells times the wave function squared. That's what I've been talking about. So now we're ready to look at a different one of these hydrogen orbitals. So in this case, we're going to have n equals 2. But remember, if n equals 2, then L can be equal to either 0 or 1. So if L is equal to 1, we're looking at p-type orbitals. So this is an L equals 1, and then m sub L can take on 3 different values. I'm just going to list them here in parentheses. L could be -1, 0, or +1. So those are the possible m sub L values. And so we're going to have 3 different wave functions corresponding to these 3 different m sub L values. But these are all L equal 1 quantum number, and that means that these are what we call p-type orbitals. So L equals 1, our code is P. So here's a little picture of the radial distribution plot. So it looks kind of like the radial distribution plot for the 1s orbital. So it says 0 probability finding it in the shell right at the nucleus because that shell has 0 volume. But as you move further away from the nucleus, there's a peak in probability. So this would be sort of our most probable location right at this peak. So that corresponds to a little bit higher than 2 times 10 to the minus 10th meters. By the way, there's a useful unit that I'd already talked about. I'll go ahead and write it in here. It's called the angstrom, and it's given this symbol, a capital A with a little circle on the top. And 1 angstrom is equal to 1 times 10 to the minus 10th meters. It's a useful unit when you're talking about atoms because the radius of a typical atom is about an angstrom, about half an angstrom, something like that. So somewhere on the order of an angstrom. So this is a useful atomic length scale, so we'll often talk about angstroms. So these numbers here, times 10 to the minus 10th meters, are really angstroms. All right, so what do these P's look like? So here's one of them. This is actually for the one with m sub L equaling 0. And this is what the shape really looks like. Kind of this squashed balloon. It's a little bit flatter on this side. It's kind of bowed out on this side. And it's shish kebabbed by this z-axis right here. So we have to give directions when we're talking about the atom. So we lay down these 3 axes, an x, y, and a z-axis. And so this balloon shape is skewered by this z-axis. So for that reason, instead of calling this the m sub L equals 0 wave function, we're going to call it the pz function. Z because it's skewered by this z-axis. So we call that the z function. We chemists don't actually draw the correct shape very well. Usually just represent it as kind of 2 balloons tied together, or 2 dumbbells. And you can draw this, you can sketch one of these out really easily by putting an axis down, giving it a label. Oh, I'm going to call that the z-axis. Draw a little dot. That's where your nucleus was going to be, so that's the origin of your axis. And then you just draw a little balloon shape that's kind of shish kebabbed by the axis. Okay, so I got mine a little off symmetry there, but you get the idea. So that's the balloon shape. So these are the contour plots then for the 2p orbital. So where are you most likely to find an electron? Well, inside this balloon somewhere. That's the most likely location. But it could also be down here in this lower portion, right? Now, right on this plane, right here, that turns out to be what we call a nodal plane, N-O-D-E, node. We're going to add an A-L at the end. So this is a nodal plane. So just like nodes that we talked about before, that's a region of 0 probability. This node happens to have the shape of a plane, though. So anywhere on this plane, the probability of finding the electron is absolutely 0. So again, we have that funny question, well, why is it likely to find the electron up here or maybe down here, but never in between? So how does it get from one side to the other? You can't ask that question. Anyway, just the way it is in quantum mechanics. So these 2p orbitals then have these funny sort of dumbbell shapes to them. And because they're these different m sub L values, we can relate them to these other shapes. So there's a orbital that's kind of shish kebabbed by the y-axis right here. We call that the py orbital. There's another orbital that's shish kebabbed by this px, by this x-axis right here, and we call that the px orbital. So there are 3 different wave functions corresponding to these 3 different m sub L values, m sub L -1, 0, and +1. And we're going to call those pz, px, and py. And so here they are shown on one set of axes. And you could draw any of those that you wanted. So if on a quiz or something I asked you to draw, like say, a px orbital, here's what you would draw. You would say, oh, well, Here's my x-axis, here's the origin, and a px orbital just looks like two balloons that have been shish kebabbed by the axis. Where are you likely to find the electron? Well, somewhere inside that balloon shape, but never along this node that runs through there on that dotted line. Now here are the d orbitals. So the d orbitals happen when we've got n equal 3, and the possible values of L can be 0, 1, or 2. So we've already talked about the L equals 0 being the s-type orbitals, and the L equal 1 are now the p-type orbitals, and the L equal 2, these are going to be the d-type orbitals. So if L equals 2, m sub L can take on these values, -2, -1, 0, +1, and +2. Right? So those are the possible values. And so there are 5 of those. So for the orbital, the wave function that has n equal 3 and L equal 2, there are then 5 different wave functions corresponding to these 5 different m sub L values. What do they look like? Well, they look roughly like these pictures. So we're going to go through and look at those. Again, here's the contour plot for the actual shape of one of these orbitals. Again, we've laid down some axes. Right here in the center at the origin of our axes, that's where the nucleus of the hydrogen atom is going to be, where I just drew that blue dot. This particular orbital is called the dyz orbital, and we'll see why that is in just a minute. So you end up with these sort of lobe balloon shapes, look kind of like clover leaves, and they're here in between the axes, so in between the z-axis and the y-axis. Again, we don't really get these shapes right as chemists. We usually sketch them so they look like balloons, but this is a real better representation of what they might look like if you were to draw the actual contour plot. Again, here's the radial distribution plot. So again, we have a most probable shell right out here at about 5 angstroms. So there's our most probable distance. And then the distance goes down as you go either towards the nucleus or away from the nucleus. So looking at this picture, this is called the dyz orbital. Why is it called the dyz orbital? Well, because there are axes. These are kind of located, these lobes are located in between the z and the y-axes. So they're kind of, if you imagine there's a plane kind of right through here, they're on that plane in between the axes. And so this next one is called dxz because there's an x-axis and a z-axis, and these 4 lobes are kind of in between those x and z axes. Then we have another one called dyz. And again, these lobes, these cloverleaf shapes, flower petal shapes, are in between the x and y axes. Now this one's kind of funny, and it's called d, and the subscript on it is x squared minus y squared. And if you notice, the cloverleaf shape is shish kebabbed by the x-axis and the y-axis. So that's how you can remember this funny label is telling you which axes get shish kebabbed, okay? And then finally there's the funniest looking one of all, and that's called dz squared. So there are 5 orbitals, 1, 2, 3, 4, 5, corresponding to these 5 different m sub L quantum numbers. And here's this last one, dz squared. So you'll notice that the balloon shapes get shish kebabbed by this z-axis. But in the xy plane, there's also this funny little disc shape. It looks kind of like a disc shape here. A better representation might be a little donut. So it's kind of like a little ring. And then right here at the middle, there's a hole of 0 probability. So there's a node, again, right here in the middle, right where the origin is. So that would be the hole of your donut. So this is kind of a donut shape down there. Technical name would be a torus if you're into fancy names. And here all 5 of the d orbitals put on one set of axes. So you see, we always think of atoms as balls, as spheres. Well, when we include all of these orbitals, then it still kind of has that spherical symmetry about it, right? So roughly speaking, when they're grouped all together, it still has that ball shape. So I might ask you on a quiz or on a test or something to sketch a d orbital. How would you go about doing that? Well, here's what you would do. So if I ask you to draw the dxy orbital, then here's what you would do. So you lay down some axes. So I'm going to draw some axes right here. We know that right here is where our nucleus is. I'm going to label one axis x and one axis y. So these xy pairs, we know that the little flower petal shapes are in between the axes. So I'm just going to draw 4 little petals, in between my axes here. So that would be the dxy orbital. Then if you have to draw something more complicated like dz squared, then you lay down some axes like this. We're going to call that the z-axis because we know in dz squared the balloon shapes get shish kebabbed by the z-axis. So that looks a little bit like a pz orbital. And then we have to go in here and be kind of really clever and draw this sort of donut shape that goes around the middle here. And so there's an example of how you might draw a dz squared orbital. So really it's just those two shapes. The cloverleaf shape, you just have to change the orientation, and the funny shape with the balloons and the donuts. Now I won't ask you to memorize these, but if we look at the next orbital, so we have n equal 4, and then L equals 3, then our m sub L values could be -3, -2, -1, 0, +1, +2, and +3. So that would correspond to the different values that we could put here for m sub L, and that would give us 1, 2, 3, 4, 5, 6, 7 different orbitals. And remember, when F stands for L equals 3, quantum number L equals 3, and so there's 7 of these F orbitals. And here's one of those F orbitals where you've got these balloon shapes sort of pointing up into these different quadrants in space. So notice kind of what we've done here. If we go back to the S orbital, which looks like a ball right here, if you were to pinch this ball in the middle, what would you get? You'd get 2 lobes, right, like this. Yeah. So you'd squeeze it in the middle, like put a rubber band around it, and squeeze it off into 2 lobes. Now if we take each one of these lobes and we squeeze it again, what do we get? Yeah, we get 4 lobes. Then if you take one of these 4-lobe guys, like this one right here, and you pinch that guy, what are you going to get? Yeah, you're going to get more lobes, right? So each time we're just sort of increasing the number of lobes. So you can kind of get an idea and imagine in your head how complicated the G orbitals might look like if we were to visualize those. Alright, so now we have looked at all the different types of possible orbitals, and we've seen some of the different representations using dot plots, using contour plots, radial probability distribution plots, and these different shapes. So you should be able to know now something about the shapes. So I'm going to talk to you real quickly before we finish up here about an alternative interpretation for the quantum numbers. So this n quantum number that we call the principal quantum number, what it does is show you distance from the nucleus. So the difference between a 1s wave function, it's just a small ball, and a 2s wave function is just size, or average distance from the nucleus. Similarly, if we were looking at a 2p orbital, then it would be this sort of small balloon shape, whereas a 3p orbital, you guessed it, would just be bigger balloons. So the chances that you can get further away from the nucleus increase. So n always tells you something about average distance from the nucleus. The bigger n is, the further that hydrogen atom electron is away from the nucleus. Now remember, L tells us something about shape. So the s orbitals right here, when L is equal to 0, they're all shaped like sort of this ball shape. When L is equal to 1, we're talking about p functions, and they're all shaped like these dumbbells. And then finally, well, not finally, but then we have L equal 2, those are the D functions, and they look like the 4 flower petals, the clover leaf kind of shape, mostly, except for dz squared. All right? And then finally, the m sub L is going to tell us about orientation, right? So for the p orbitals, for example, we have these 3 m sub L values, -1, 0, and +1, and they tell us that these orbitals are oriented in these different directions. Okay, so along a y-axis, along a z-axis, and along an x-axis. So the m sub L value is telling you, okay, you take that shape, how can you rotate it in different ways in space? So those are different interpretations of these 3 quantum numbers. Distance from nucleus, the shape, where you're going to find that guy, and the orientation, how it's twisted, turned in space. Finally, let me remind you about energies. So energies also only depend on the principal quantum number. So right here, here's a drawing of what we call an energy level diagram. So it shows energy on this y-axis increasing, and then it lists each of the orbitals that we can see. So the 1s orbital is right here, so it has n equal 1, so that's the lowest energy orbital. N equals 2, we're now at a higher energy, and so the 2s and these 3 2p orbitals, why are there 3 2p orbitals? Well, they correspond to the different m sub L values. Let me just go through this again. This is telling us that our n value right here is 2, The letter here is telling us that our L value is equal to 0, and there's only one of those orbitals because m sub L can only ever be 0. Now in this case, we've still got n equal 2, but now L is equal to 1 because it's p. And since L is equal to 1, then these three little lines right here represent m sub L equaling -1, 0, and +1. So each little line right here represents a different wave function with its own set of values. So like 2, 1, and -1. All right, so its own set of quantum numbers. So each one of these is a different orbital. It's going to have a different orientation. So there are 3 2p orbitals, but have exactly the same energy as the 2s orbital. So orbitals that have the same energy, we use a special term for those. We say that they are degenerate. So it doesn't mean that there's any kind of moral failure on them. They're not good for nothing orbitals. No, it's not that kind of degenerate. We use it in quantum mechanics to describe orbitals that have the same energy. So we would say that the 2s and the 3 2p orbitals are all degenerate. They all have the same energy in the hydrogen atom.